Now there is another important characterization that we do for sequences, and that is the property of boundedness. Okay. Boundedness. This is a very important property, and it's described as follows. A sequence which is described by a set of numbers x of n can go from minus infinity to infinity. This entire sequence is said to be bounded. Said to be bounded. This is a very, very important property. If every x of n, for all values of n, we can say that there is a upper bound in terms of its numerical value. We say that that's equal to bx, and this upper bound must be finite. It cannot be infinity. Then every signal will be there. So for example, if I have a sinusoid with amplitude 1, then I say that this particular sequence is bounded by the value 1. B of x will be equal to 1. Okay, so that's exactly what we want to. So if I have an example, a times cosine omega naught n plus phi, if this is my x of n, then by looking at this expression, then I know that mod x of n is always upper bounded by cosine term will always have a maximum value of 1, upper bound will be a. So because of this property, we then say that x of n is bounded. In this particular example, x of n is a bounded sequence. On the other hand, if I look at another example where x2 of n is equal to a times alpha power n u of n, where alpha is greater than 1. Okay, x of 1 will be a alpha, x of 2 will be a of alpha squared, alpha cube 4, and so on. But alpha power n is a growing exponential. So you will never be able to find a upper limit which will bound all of the amplitudes. So this particular example will be an unbounded, or x of n is not a bounded signal, is not bounded. Okay. Very important that you are able to clearly classify these signals. All right. So let's take a quick example, and then we will look at it and then see if we are able to characterize this. So one aspect is the aspect of boundedness. Let me just give you a couple of more definitions, and then we will move on to examples. There is a property called absolutely summable. Absolutely summable. Okay. Now a sequence is said to be absolutely summable if summation n equal to minus infinity to infinity modulus of x of n. So basically you are taking the modulus of each sample of the sequence and summing it from minus infinity to infinity. And if this is less than infinity, then you say that this is an absolutely summable sequence. Okay. Give me an example of a sequence that will not be absolutely summable. Any periodic sequence, right? Any periodic sequence, when you do the summation, it will go to infinity. X of n may be bounded, but when you do the summation, so it's not absolutely summable. Periodic signals will not. So ideally what you would see is the energy signals are the ones that are also likely to be absolutely summable. Now there is another term which is also useful for us, which is called square summable. Square summable. This says if the summation n equal to minus infinity to infinity, mod x of n squared is less than infinity. Okay, then that signal is called a square summable. This is clearly the definition of an energy signal. Okay, an energy signal says E of x will be less than infinity. So this is exactly an energy signal. So basically, energy signals are those which are square summable and also will be absolutely summable. We can look at that, but periodic signals will not satisfy either of those either of these two conditions. So this is also a useful principle for you to keep in mind. All right. So now we want to expand on this and also look at some examples. So let me quickly bring you a few examples which will be helpful to build up the concepts. So here is the understanding of a bounded sequence. A bounded sequence is one where you have an upper bound on the each sample. So basically, you look at x of n over all examples or all the sample values. So let us take another example, and we will quickly look at that. Okay. Now, if I give you a sequence which is given by example y of n equal to, so basically we are looking at the aspects of bounded sequences. Okay, we are trying to get comfortable with that. Y of n is equal to summation k equal to 0 through infinity rho of k raised to the power k x of n minus k. Okay, so you can say that we are given that x of n is bounded. X of n is bounded. The question that is being asked is y of n bounded? Will y of n be a bounded sequence? Okay, so that's what we are going to apply. So basically, we are going to be looking at modulus of y of n. Right? That's, we want to know whether that is going to be bounded. So let us take it one step at a time. So let's write down a few terms. This will be helpful for us. This will be x of n plus rho times x of n minus 1 plus rho squared times x of n minus 2 and so on. Okay. So when you have a term which is like this, a equal to b plus c, if you have any expression of this form, then modulus of a is equal to modulus of b plus c. But if I take the modulus inside, then this becomes an upper bound, less than or equal to modulus of b plus modulus of c. So this is a well-known result from algebra which you want to utilize in this expression. So y of n is equal to a series of terms containing x of n. So we can write this as an upper bound. So y of n upper bound, write this as an upper bound, is less than or equal to the modulus of each of the individual terms. So modulus of x of n plus rho times modulus of x of n plus 1 plus rho squared times modulus of x of n plus 2 and so on. So basically you will get these. Okay. And we know that each of these terms is upper bounded, it's a bounded sequence. So basically the bound is equal to bx. So this is less than or equal to bx, this is less than or equal to bx, this is less than or equal to bx and so on. So we can say that this upper bound can further be written as, wherever there is the modulus term, you write it as bx. Then what is left? You will be left with 1 plus rho squared all the way to infinity. Okay, that's a geometric series where if we are given that rho is less than 1, rho greater than 0, less than 1, then if it's greater than 1, it's a expanding series, so it's not useful. So given that rho is, so this will be a convergent geometric series, b of x 1 over 1 minus rho, and we are able to say that every value of y of n must satisfy this limit. So, in other words, we can call this particular term as by and then say that y of n is always bounded by by, and therefore, this implies, this is for all values of n, this implies that y of n is a bounded sequence, is a bounded sequence. Okay? Good. Now, maybe after a difficult example, let me give you a very simple example. You will find that this is very, very trivial and straightforward. Okay, if I have y of n, this is the averaging filter which we have talked about, 1 by 3 times x of n plus x of n minus 1 plus x of n minus 2. Okay, some just interesting observations. This is the averaging filter, 3-tap averaging filter. Okay, is this causal? Output depends on past current and past inputs, so it satisfies the property of a causal filter. Okay, and we also explained in the last session that this is an LTI system. LTI system means there must be an impulse response. So, what is the impulse response of this particular system? There are 3 non-zero taps, 1/3, 1/3, 1/3, and then zeros. Origin is here. Okay. There are no non-causal taps, so basically it is 0 before this, only at n equal to 0 you have 1/3, and then n equal to 1 1/3, n equal to 2 1/3, and this is, so basically we have a causal sequence. These are all interesting things. So, we are given that x of n is bounded. That means mod x of n is less than or equal to bx for all values of n. Okay. Is y of n bounded? Modulus of y of n will be less than or equal to 1/3 modulus of x of n plus modulus of x of n minus 1 modulus of x of n minus 1 plus modulus of x of n minus 2. Okay. Notice that I have changed from equality sign, I have changed it to less than or equal to, because that is a property of the modulus. Now, each of these can be replaced with b of x. B of x, what I mean is less than or equal to b of x, less than or equal to, less than or equal to b of x. So, this b of x, if you bring it out, b of x 1/3 b of x, I will get 1 plus 1 plus 1. So, which means that the upper bound happens to be b of x. So, and we can say that y of n is a bounded sequence with the same bound. Why? Because I did not do any operation except averaging. So, if the original sequence was bounded, this one also will be bounded, and of course, whatever was the bound of the original sequence is also the bound of the current sequence. Okay, so y of n is a bounded sequence. So, I hope you are able to see that this is a useful way of understanding what the so now this leads us to a very important principle which I have introduced, in a very simple way through these examples. Now, what we have is the following. Okay, we have introduced the notion that you can look at the boundedness of the input and then make a comment about the boundedness of the output. So, when it comes to a discrete time system, there is a very important property which is called bounded input, bounded output stability. Bounded input, comma, bounded output stability. Okay, and let me explain what the name means. This is often used with the acronym BIBO, bounded input, bounded output. and this is a primary mechanism for discussing a form of stability. Okay. What it says is, if I give you an input that is bounded, will the discrete time produce for me an output that is also bounded? Okay. If the answer is yes, then you have these systems will satisfy a bounded input, bounded output stability condition. Okay. So, was this particular example y of n equal to 1/3 of x of n plus x of n minus 1 plus x of n minus 2, BIBO stable. This discrete time system is BIBO stable because the input is bounded, then BIBO stable, or BIBO stability is also fine, BIBO stable. And the previous example that we looked at, okay, this is also a BIBO stable system. At that time we did not look at it as a condition for stability, but we can now come back and say that this is also a BIBO stable system. Okay, now comes another very important application of the concepts that we are talking about. Now, if it turns out that it is an LTI system, okay, an LTI system is one which is characterized by an impulse response H of n. Input-output relationship is given by y of n is equal to summation k equal to minus infinity to infinity h of k x of n minus k. Notice which one am I time reversing? Input. What is not being time reversed is the impulse response. And again, it does not matter because the same expression can also be written as k equal to minus infinity to infinity x of k h of n minus k. Okay, I'm going to use this form because there is an advantage for me in the context. Now, supposing I am given that x of n is bounded. Okay, x of n is bounded. That means mod x of n is less than or equal to some constant which is less than infinity, some finite value b of x, and all input samples are bounded by this value, and this holds for all values of n equal to minus infinity to infinity. This condition will be satisfied. Now, my goal is to find out whether this LTI system, which has this input-output relationship, given that I am supplying a bounded input, will it produce a bounded output? So, I want to look at modulus of y of n. That will be equal to the modulus of what is on the right hand side, k equal to minus infinity to infinity h of k x of n minus k. Then, using the property of modulus, I say that this is less than or equal to summation k equal to minus infinity to infinity modulus of the individual terms h of k x of n minus k, and this is nothing but, when you take a modulus of product, it is the modulus of those individual terms. This is less than or equal to summation k equal to minus infinity to infinity modulus of h of k modulus of x of n minus k. And modulus of n minus k, because it is a bounded sequence, we know that this is always less than or equal to bx. So, substitute for that, pull bx outside, what you will get is this is less than or equal to bx summation k equal to minus infinity to infinity mod h of k. Now, if y of n has to be bounded, that means it must be less than or some constant. B of x is already a constant. So, the only thing that needs to be a constant will be bounded is this. So, what we are saying is, if k equal to minus infinity to infinity mod h of k is less than infinity, that means it is some finite value, then let us say that that finite value, if you say, is equal to a. So that means let's say that this is less than or equal to a, which is less than infinity. This is the condition for absolute summability. Absolute summability, right? When we said, when you take each of the sequence, take the absolute value and then sum it up, that is the condition for absolute summability. Now, if the impulse response is absolutely summable, then the input is bounded, then the output is guaranteed to be bounded in the following manner: mod y of n will be less than or equal to a times bx, and which means that y of n is also bounded. Okay, very powerful result, because what it says is, if you want to characterize an LTI system and see whether it will produce unbounded output, you don't have to try all possible inputs that are there in the world. All you need to do is look at the impulse response, see if it is absolutely summable. If it is absolutely summable, then this LTI system will not produce for you unbounded output. As long as the input is bounded, the output will always be bounded. So what we have done now, let me just quickly summarize. We defined the notion of boundedness. We defined what is absolutely summable and square summable. Then we looked at individual sequences and said, okay, how do I check whether a particular sequence is bounded? Look at what is the expression for the sequence and see if you can get the value, and then you decide whether the given sequence is bounded or not. And so we looked at a couple of examples. Now, if the input is bounded and the output is bounded, then such systems are called BIBO stable, bounded input, bounded output stability. That is the condition under which these systems will not produce an unbounded output as long as the input is bounded. Now, the final step is, if we are talking about an LTI system, then this particular LTI system is characterized by an impulse response, and so I don't need to look at the output. I can straight away look at the impulse response and see if it is absolutely summable. If the input is absolutely summable, then I have a system that will be which will also be BIBO stable.